Test, 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 test. Hey, Jack. All right, in order to answer your question, we have to talk a little bit about a couple of different concepts. So I'm going to quickly talk to you a little bit about Newton's law of gravitation, second law of motion, third law of motion, and a little bit about reference frames, because your question actually involves a lot of different concepts. And so we're going to kind of look at each of the concepts individually, and then hopefully that'll help provide you with the correct string of logic to work yourself through the situation that you've created. So the first thing is Newton's law of gravitation. So this is a law that tells us the force of attraction between bodies that have mass. So here we have a diagram. We have the Earth, we have the Moon, and we have a moose. And the attraction that these three things have is due to their mass and their separation from each other. So the Earth, we can see the Earth has a mass of 5.98 times 10 to the 24th kilograms, and it has a pretty sizable distribution of mass. So its radius, if we were to think of the Earth as a sphere, which it's not really, it's more like an oblique spheroid, it's squished a bit, but if we were to approximate it as a sphere, which is pretty accurate for what we're going to be doing, then its radius would be 6.38 times 10 to the 6th meters. If we look at the Moon, we can see that it has a mass of 7.35 times 10 to the 22nd kilograms, which is about 2 orders of magnitude less than the Earth. And it has a radius, or an average radius, of 1.74 times 10 to the 6th meters. So those are relatively big numbers compared to things that we would commonly find on Earth, like a moose. The moose, by comparison, is about 22 orders of magnitude smaller than the Earth at just 270 kilograms, or 2.7 times 10 to the 2nd kilograms. And if we were to approximate the moose, just for simplicity in this case, as a sphere of meat, then its radius would be about 1.7 meters for the average female moose. So we can see that, again, these numbers are pretty important in understanding what's going on here, because they're so drastically different from each other. So let's consider for a second just the Earth and the Moon. So the Earth and the Moon are separated by an average distance of 3.8 times 10 to the 8th meters. If we take the mass of the Earth, the mass of the Moon, their average separation from their centers of mass, so in this case the center of mass of the Earth would be somewhere in the center, and the center of the mass of the Moon would be somewhere in the center. And that's what we're talking about when we're talking about the separation between the two bodies, as far as Newton's law of gravitation goes. So if we look at the law of gravitation and we calculate the force of attraction between the Earth and the Moon, or the Earth and the moose, or the Earth and something on the surface of the Earth, then we'll get some numbers that we can actually look at. Now, one of the things that you had said in your video to me was that objects, your two example objects falling towards the Earth, would fall at a rate of 9.8 meters per second squared, and that would be the acceleration due to the gravitational attraction of the Earth. And that takes us back to Newton's second law. So Newton's second law says that the net force acting on an object is equal to its mass times the resulting acceleration that it would feel. In this case, just for simplicity, if we're just going to imagine something near the surface of the Earth, then let's ignore all of the other forces except for the force of attraction from the Earth. So in this case, the net force is just going to be the force of gravity due to the Earth acting on some object, maybe a moose standing on the surface of the Earth. And if we solve the Newton's second law for acceleration, then we would find that if we divide the weight of the moose, or the force of gravitational attraction on the moose, divided by its mass, we'll get its acceleration, the acceleration it would feel if it was in free fall or falling towards the Earth. And the resulting equation would be capital G, which is a constant. You can see that over here in my notes. Capital G is the gravitational constant at 6.67 times 10 to the negative 11th newtons meters per second divided by kilograms, or sorry, meters squared divided by kilograms squared. We have two masses and the separation squared for the force of gravity. So if we were to divide one of the masses out here, then we would be left with just the gravitational constant, the mass of the Earth, and divided by the separation of the two things squared. If something is sitting on the surface of the Earth, then the separation between those two objects is very nearly the radius of the Earth. And that approximation comes out to be very accurate, considering the order of magnitude difference between how tall an average moose is and the radius of the Earth being 6, 7, 8 times in orders of magnitude larger. We can see that. So the moose is 1.7 meters, and the radius of the Earth is 6 orders of magnitude larger than that, about. So that approximation is very accurate. No need to worry about the added height of the moose. Anyway, if we put that into a calculator, got a calculator over here. We put that into the calculator, so here I have the gravitational constant, the mass of the Earth, and the radius of the Earth, and we can see that the number we get is about 9.79909. So it's just about 9.8 meters per second squared, based on our approximation. So that's where that number comes from, and that's only true for objects in free fall near the surface of the Earth. So the next question is, well, what about, let's say the moose is at the International Space Station. Well, the International Space Station is 330 kilometers above the surface of the Earth on average. 330 kilometers is still relatively small compared to the radius of the Earth. So it's not correct that people in the International Space Station are weightless, which is another question for another time. So the acceleration due to gravity of people or a moose in the International Space Station is about 8.86 meters per second squared, or about 80% the acceleration due to gravity of something on the surface of the Earth. So astronauts, or mooses, at the International Space Station are not weightless. They're actually in free fall, and they're falling about 80% the rate of something that is closer to the Earth. So let's look at, so hopefully that answers the first question. When we consider things falling towards other objects, we need to think of Newton's law of gravitation. So now we know we've got something, and we know how to calculate the acceleration that it might have based on the force of gravitational attraction. So let's look at something else here. Let's simplify the system, and let's just have two objects in space separated by some distance r, and we'll say that one has a mass of mass 1 and one has a mass of mass 2. So Newton's law of gravitation would be that the force of gravity felt by them both would be the constant g times their two masses divided by their separation squared. And the reason I say that they both feel the same force of gravitational attraction is due to Newton's third law, which is that every force has an equal and opposite reaction. So if mass 1 is pulling on mass 2 with some force, mass 2 pulls on mass 1 with that same force. And actually we can see that in the symmetry of Newton's law of gravitation. If I were to switch these two masses, well, we know from basic algebra that switching the order of two products does not change the answer. So we can guess that the forces they both feel would be the same. Now, the interesting part comes in the last part of your question, which was you're looking at objects of different sizes falling towards another object of a different size, and this is where Newton's second law is important. So if we try to find the acceleration due to the first object over here, then we would need to find the force of gravitational attraction on that object, which is this, and we would divide its mass. And this is what you are referring to as inertia. All things with mass have inertia. Inertia is a property of matter, and it comes into play in motion because things with a lot of matter tend to resist changes in their motion. Algebraically, we see that this proportionality between the acceleration that we get out of a force is related to the amount of mass that something has. So if mass 1 is relatively large, the acceleration we get is going to be small, and if mass 2 is relatively small, then the acceleration we would get would be very large. So let's do a more concrete example. So we're going to ignore the moon for now. We're just going to look at this moose. We're going to say it's somewhere around the International Space Station. And we're going to look at these two objects. They exert the same force on each other. So what will their accelerations be as they careen towards each other? So the force acting on the moose by the Earth is given by Newton's law of gravity. So this would be the gravitational constant, the mass of the Earth, the mass of the moose, divided by their separation squared. And here I've got this as being the distance from the center of the Earth up to about the altitude of the International Space Station. We'll use that calculation later. The force acting on the Earth by the moose also has mass. So the moose is going to attract any other object with mass, including the Earth. So the gravitational force acting on the Earth by the moose is given by almost the same equation, except here the mass of the moose comes before the mass of the Earth. Those calculations algebraically would be equivalent to each other. So if we take the force of gravitational attraction between the moose and the Earth, and we divide it by the mass of the moose, from Newton's second law, we should get an acceleration. And the acceleration we get is the same that we were looking at earlier. It's 8.86 meters per second squared, and that's the acceleration due to the gravitational force of attraction between the moose and the Earth. The interesting thing happens when we try to find what the acceleration of the Earth is due to the moose. Now remember, the moose is exerting the same strength or same magnitude force on the Earth. However, the Earth is way more massive. And so in this case, the acceleration of the Earth is 4 times 10 to the negative 22nd meters per second squared, and that is a very, very small number. But it does not necessarily mean that the Earth does not move at all. If we were to actually look very carefully at any two orbiting bodies, if we say the Sun and the Earth, or the Earth and the Moon, in those situations, the two planetary objects have vastly different masses. And so we might have the Moon in this case that is traveling around the Earth. And that's due to, again, the force of attraction between them and that acceleration that is providing that elliptical path. However, if we were to look very, very closely at the Earth, or if we were looking at the Earth-Sun system, we look very closely at the Sun, we would see that the Earth is moving. It is not sitting